This is Group B, FRQ number 2. So for A, we're asked to calculate the value of hydrogen, the concentration of hydrogen in an HOBr solution that has a pH of 4.95. So find the pH, we have to take the negative log of it. But since we're given the pH, we would have to take the anti-log of it. So it would be 10 to the negative 4.95, and you plug that into your calculator, and you would get 1.112 times 10 to the negative 5. And then that would be your hydrogen concentration. Okay. And then for V, we're asked to write the equilibrium constant expression for the ionization of HOBr in water. So then we will have to put products over reactants and look at the equation above. So then products would be H plus and OBr products, and then reactants would be over HOBr, and that's what we have right here. And then we're also asked to calculate the concentration of HOBr in an HOBr solution that has hydrogen concentration equals 1.85 times 10 to the negative 5. So then we would have to draw a nice table. Since we're given this, we would put 1.85 times 10 to the negative 5 polarity. And we could assume the same thing, because since they're on the products side.
Whoa, no.
And then right here we could just assume that it's 0. And then for the change, since the values it's changing, we will have to like add x and subtract x. So since H and OBr they're on the same sign, that would be plus x. And right here would be minus x, since it's on the different side of the equilibrium sign. So then right here would be 1.8.
You can assume that they're negligible because the x is going to be really small. So yeah.
So then since we're also given the Ka value over here from earlier, we could plug it into this one to solve. So 2.3 times 10 negative 9 equals products, which is 1.8. So since it's like the same thing right here, we could square it over x. And then once you do your calculations, you'll get x equals 2.14.
In letter C, part 1, we need to calculate the volume of BaOH2, and we need to calculate how much volume is needed to titrate the HOBr. So to start off, we are given 0.115 polarity of BaOH2, and we're not given the volume. This is added to 65 milliliters of 0.146 molarity of HOBr. So to start off, we need to write an equation, a balance equation like this. If you don't write a balance equation, you're not going to put the 2 here, so your answer is not going to be correct. So to start off, we're going to do M1 P1 equals M2. So we're going to put the given. Molarity. We don't know of volume. Then we're going to have to double this because there's 2 of them. So we are getting 100.
So for problem A,
30
the letter A, we have to write the
milliliters. And we are given 0.292
equal to H plus.
Now we divide.
And we can follow for that equation. We have to calculate what the value is, and since we're given the 0.50,
Our volume
plug that in.
equals
Molarity.
41 mil.
And then we have zeros. We're not giving any. Are you ready for these two? And then we have to minus x, then add x. And then you bring it down. Ready?
In letter C, part 2, we need to indicate whether the pH at equivalence points is basic, acidic, or neutral. So at the beginning of this problem, we were given that Ka equals 2.3 times 10 to the negative 10. This is good for us because we can plug into this equation right here for Kw and solve our Kb, which we'll later use to find pH. So right now, we're going to divide both sides by 2.3 times 10 to the negative 9th to get Kb. And we got Kb equal to 4.3 times 10 to the negative 6. Well, this we're going to plug into this equation right here. pH equals 14 plus log of Kb to get our answer. So 14 plus log 6. And we get our pH to equal 8.63. Because pH is 8.63 and it is greater than, which is greater than 7, this problem right here will be basic.
The second FRQ, we are looking for the moles of NaOBr. And we're given the milliliters of and the molarity of HOBr. And so we convert this to liters by moving it 3 decimal points over. And then we're given the buffer of the H plus ion, which or the concentration, which is 5.0 times 10 to the negative 9, and there's no volume change. So using this information, we are going to write the Ka expression. And so since we're looking for this, we are going to derive the equation to make it equal to that. And then we're going to divide, so we multiplied by the concentration of HOBr, and then we're going to divide by the concentration of H plus. So we're left with 1 times OBr. So this is our final derivation of the equation. And then we're going to plug in the values that we have. So the buffer over here, the Ka, which were given in the previous problem. Okay, so we plugged in the values to the expression that we derived, and so we get 0.074 moles over liters of the OBr. And so to find the moles, we multiply that by liters. The liters cancels out, and we're left with 9.2 times 10 to the negative 3 moles. So for part E, we're asked to determine why HOBr is weaker than than HBrO3 in terms of molecular structure. So if you count the valence electrons of this compound, it has 14. So to draw the molecular structure, you need to have 14 valence electrons.
We have to plug in what we're given to try to find out.
So you would draw
So
the 3 elements, and then you would draw their valence electrons. So hydrogen has 1, oxygen has 6, bromine has 7. So then you would draw the bonds accordingly. These 2 electrons would make a bond, and then these 2 electrons would make a bond, and then all of these electrons would be lone pairs because they don't. This allows you to have 14 valence electrons. So the molecular structure would look something like this, and they would be at bent angles this way. So this doesn't have the oxygen and the hydrogen don't bond. and so it's weaker because the bromine doesn't, it kind of sets it off balance, and so it's not as strong because this is very polar, and so it makes it strong, weak. And so for the HBr, we need 26 valence electrons, and the structure would be drawn like this. And so since the O and the H bond together, it makes the hydroxide, and that makes this a stronger acid because it like balances everything else. And so the way that this is drawn, there are 26 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14. 5 to 6. So there's 26 valence electrons in this structure, and because this side of the structure is so like it off balances, then it's a stronger acid.